Okay, so here is an example of a direct proof where we're going to talk about what happens when you set up a proof and you get stuck and how we can consider other items. So here we have a situation that we want to prove that n cubed minus n is divisible by 6 for all n where n are integers, right? So you could do this by induction, and you may be more comfortable doing this by induction. But many times students will say, oh, well, I can do a direct proof, and really I just need to consider when n is odd or when n is even. And I want to warn you that even though that approach for a direct proof can be beneficial in many cases, there are situations, such as what we'll see here, where we are limited in our work. So if we were going to go through this approach, we could say, hey, let n equals 2k plus 1. Because when I'm doing a direct proof, I'm going to let my values be what they are. When I'm doing a proof by contradiction, I'm going to assume my values are what they are to get to a contradiction. So here I'm going to let n equals 2k plus 1, and technically I should say that k is going to be an integer, which is going to tell me that n is odd. Right? So substituting n for n cubed, right? N into n, this is what we get. Expand the binomial with the coefficients 1, 3, 3, 1. First term cubed, 3 times first term squared, second term, 3 times first term, second term squared, plus second term cubed, right? And then minus 2x plus 1 gives me this negative 2k minus 1. So if I put things together, I have 8k cubed plus 3 times 4k squared plus 6k, and then minus 2k because the plus 1 minus 1 cancel, right? Which then gives me a form that's factored, but nowhere is this getting me divisible by 6. Right? We don't know it. And so we might say, okay, well, I'm stuck here, but let me try the other approach with n is 2k, right? Let's say n is even. So let n equal 2k. Once again, if I have a direct proof, I'm going to say let my values be. So n is going to be 2k, k is an integer, so n is even. Substitute in to n cubed and n, and I have 2k cubed minus 2k, which gives me 8k cubed minus 2k. And once again, divisible by 6. I don't know. So you may get stuck on proofs, and that's okay, right? It allows someone to see that you at least understand approaches that you can use. Not expected for you to be able to prove everything the first time, all the time. But when you get stuck, let it lie, or think of another way that you could do your work. So let's think of another way that I could work with n cubed minus n. So let's consider. N cubed minus n can be factored to be n times n squared minus 1, which is n times n minus 1 times n plus 1. If we rearrange, we have n cubed minus n is equal to n minus 1 times n plus 1. So therefore, n cubed minus n is always a product of 3 consecutive integers. All right. Well, if n cubed minus n is always a product of 3 consecutive integers, what does that mean for us? That means that n minus 1, n, and n plus 1 must have at least one value that is even. So therefore, with 2 as a factor, and one value, which is divisible by 3. Right? And we have to have one value which is divisible by 3. Right? Because if I have, let's say, -1, 0, 1, well, that's going to be a product of 0. That's divisible by 6. Well, what if I have 1, 2, 3? Oh, okay, well, 1, 2, 3, divisible by 2, divisible by 3. What if I have 3, 4, 5? Oh, well, divisible by 3, divisible by 2, who cares about the 5? If I have 4, 5, 6, divisible by 2, not divisible by 2 or 3, but divisible by 3. Right? That any 3 consecutive integers will have one integer that is divisible by 2 and one integer that is divisible by 3. So therefore, if I look at their product, I must be divisible by 6. So that implies that n times n minus 1 times n plus 1 must have 6 as a factor. So therefore, n cubed minus n is divisible by 6. So notice that it may be that when you first approach a direct proof problem, you got stuck, and that's okay. Right? Let it lie. Move on to something else. Come back and revisit the problem with fresh eyes, and you might find that a different way of approaching the problem leads to how you would want to, or not how you would want to, but leads to a way of getting the result. Okay? Thank you for your time.